We're very happy. We're very happy to have Gabe Moore visiting us from Yale today. He's going to be around for the rest of the day, and he's going to tell us about mechanical sensors for dark matter.
Okay. Thank you very much, and yeah, thanks for the invitation. Already, it's been great to talk to a few folks and to get a chance to chat with more folks this afternoon. So I'll be talking about mechanical sensors for dark matter, and the particular mechanical sensor I'm talking about is this little bright dot you see in the center of this picture. This is a 100 nanometer diameter glass sphere that's levitated in a laser. You can't see the laser, but it's coming horizontally in this picture. It's focused between these two lenses you do see, and you see a little bit of scattered infrared light, which are my cell phone camera picks up as purple here, but that's a 1064 nanometer laser that's holding it up just in the focus of the laser. And this little particle is going to be very well decoupled from the entire vacuum chamber and everything else around it, and we're going to be able to use it to look for weakly interacting phenomena, and I'll talk about dark matter and then some other applications we have in mind for these systems. So that's crazy. So yeah, good. So if you've heard dark matter talks over the past decades, many of them, maybe more recently this is less and less true, but many of them have been about WIMPs and axions, as folks probably know very well. But even though the vast majority of experimental work has focused on these kinds of these ideas for what particle dark matter could be, as you also know very well here, we now have this expanded theoretical view that goes beyond just our original favorite candidates of WIMPs and axions. And if you really step back and ask, what do we know from astrophysics about the properties of dark matter? It could have masses over many, many orders of magnitude in scale, not just axions and WIMPs, but all kinds of other ultralight particles that act, much like the axion, like kind of scalar fields, essentially pushing on things in the lab or converting to photons. Or on the particle side, which I'm going to be focusing on, once you get to masses above a keV or so, all kinds of different things beyond WIMPs, but that might still give you kind of a kick to some sort of sensor you have in the lab, whether that be a single nucleus, as we always did for WIMPs, or maybe in this talk I'll say a larger mechanical object. So this is a little, as an experimentalist, this is a pretty daunting picture. At least when I was in grad school, it was a much happier picture in that we could look for these, and maybe we'd see something. Now we have 20 or more orders of magnitude in mass, and there's another axis of coupling strength and everything else, then types of couplings that to explore this whole picture would be essentially impossible. There's many excellent candidates here that we basically just don't have technologies to test. And even if we knew how to test every one of these, building enough experiments to do it, because the experiments differ so much in kind of technology over this plot, could be very challenging. So faced with this, you could ask yourself, could we do a model-independent search? This is really a thought experiment, but maybe we could step back and ask that. So what would a model-independent search for terrestrial search for dark matter look like? Well, imagine you have a dark matter particle flying through the lab. You have some mass. And as we know from astrophysics, at least dark matter has to have gravitational interactions with this mass. So it should give it a little kick. It's a long-range force, so it'll give it a soft momentum impulse as it flies by. You can imagine having an array of such sensors, maybe pictured here as pendula. This thing flies through these pendula. Each of these little pendula close to it gets a little pull. And maybe you could, if you had a sensitive enough, large enough array, actually see a track through your detector from gravitational impulses. So this is a proposal from Dan Carney and all a few years ago. Now the problem is when you put the numbers to this, it's extremely daunting, as you might expect, because gravity is so weak. But you can ask, can I make these pendula still enough that I could actually see such a kick if it were to occur? And that's, can I cool them down to a low enough effective temperature that their kicks would be resolvable above their thermal noise? And if you put in the thermal noise, at least for this sort of tracking detector where you have many correlated signals on many pendula, you put in pretty heavy dark matter masses here. So sorry, this is SI units. You're going to see a lot of SI units in this talk. But this is a little bigger than the Planck mass, a sensor mass also at the milligram level, and then a millimeter spacing between these different pendula in your array, which sets the kind of impact parameter to the nearest sensors. And then to get the flux, maybe a meter-sized array. So you're doing the math in your head. That's right. That's 1 billion such sensors. You can then go put in the numbers and say, at least thermally, with the kinds of sensitivities we could get to either in ultra-high vacuum or cooling down to cold temperatures, you can get these pendula still enough to imagine doing this at least. You also have to fight against the rate, because if you're trying to make these dark matter particles very heavy, we know the local mass density of dark matter that gives us some number density and some limit on the flux. And at these kinds of Planck scale masses, let's say you might get 1 per year going through your meter square area on the Earth if we're at the average kind of Milky Way dark matter mass density.
The signal to noise has to depend on the rate in some way.
So this is event by event signal to noise. So this is if I have one single dark matter particle coming through, I'm going to have signal to noise of 100 with these parameters. So I'll just not be confused at all about a single. Yeah, yeah.
And why is it d to the fourth? Isn't it just only the nearest neighbor ones that I'm passing by, or?
Yeah, so you're counting kind of, yeah, you're basically counting that, and then you know, as you get these things denser and denser, your impact parameters are getting smaller and smaller. So, you know, if you have, you know, this is long range force, the closer you are to this, the larger the momentum transfer to the mass.
But I'm assuming that the whole thing responds, because that's where the fourth power would come from.
So no, so only the, you know, the largest impulses are being given, and your signal noise is dominated by the masses that it's passing by.
You also squared the signal to noise ratio.
Yeah, and the signal noise, sorry, this is SNR squared.
Thank you.
Yeah.
Sorry, thank you.
I have a very nice question.
Yeah.
So why is it not dependent on the volume of the
Volume of the, so the rate is dependent on the cross-sectional area of the detector. And then, you know, they've assumed this is a cube in this paper, and they count some number of sensors that this is.
Yeah, but I guess the gravity is the non-range force, right? So you need to put all the volumes.
Yeah, except that the, you know, only the nearest ones have, all the signal to noise comes from your nearest ones, because again, the impulses are largest for the nearest neighbors. And the ones that are far away, even though you will have a little push on them, you're not seeing it.
So in that, I mean, in the expression, the first expression, you've normalized the dark matter mass to like 100 times the Planck mass.
Yeah, just for a round number here, it's, you know, 30 times the Planck mass or something, 50 times.
It's a lot.
That's a lot. These are very heavy dark matter candidates. So if you went to those, I just showed you 20 orders of magnitude of mass. If you went down to the left side of the plot, this is impossible. This is asking if it's possible anywhere on that plot. And the only place, like, you should already think this is very crazy, as I'll say in a second. But the only place that you're not embarrassed to write it down is on the heavy side of the Planck mass. But, you know, nobody has, you know, no search to date has looked for a gravitational impulse in the lab, right? So this is very blue sky stuff. I'm going to get the real stuff we can do in a second, but this is maybe just setting, you know, what we would do if we could, and, you know, could dream as experimentalists. And so, yeah, the point is that if you had really, really heavy stuff up around the Planck scale, maybe you could dream about this. But the dirty laundry here isn't even this stuff, right? I mean, the dirty laundry is that if one of these things gets a kick, you have to know it got a kick. And there's fundamental limits from quantum mechanics on measuring things. And if I want to see this kick, I have to shine some photons or something at this pendulum. And there's back action from that measurement. The photons bounce off that pendulum. And it's really the quantum measurement noise that's the hardest part of doing this. And so if you were to measure the position and the momentum simultaneously of these pendula, you just couldn't do this. You'd be 1,000 times, you know, your signal to noise would be 1,000 times too low. So you need to go something like 30 dB, or sorry, this is decibels, but a factor of, you know, many orders of magnitude beyond the so-called standard quantum limit, the kind of Heisenberg uncertainty for measuring the position and momentum of these pendula simultaneously. Now, Heisenberg only told us we can't measure both. Of course, if you do your measurement in a very smart way that you're not gaining information about the position and only gaining information about the momentum, you can imagine this, but that's also way beyond the state of the art of what we can do. Okay, so this is really, really hard. Sorry, any other questions though? So this general theme is coming back.
Yeah, I have a naive question. Presumably now you don't care about if this is a fundamental particle or some composite state.
Yeah.
My question is, if this size is not 0, it's not 0.5, it's actually maybe bigger than this 1 millimeter separation, will your signal go down?
Yeah. So you'll have a form factor or something if it becomes big compared to the spacing and doesn't look point like. All that is definitely true. But, you know, even for, you know, composite particles at this size could be point like at the millimeter scale. So we'll come back to composite particles. But yeah, I think, I mean, you're the experts, but many such things in this range might be composite. Okay. So this is like the, you know, the point of showing that is just how hard it is, really. It's way beyond the state of the art of what we could do. But of course, you know, the standard thing is that we have this really complicated 20% of matter in the standard model. And then we say there's maybe one new particle in the dark sector. It's 80% of matter, nothing new. And a truly model independent thing would be to only see this, if this was at least the simplest thing you could do to account for dark matter, only see it through its gravitational interaction with the standard model. Every laboratory search we do, though, assumes that there's some stronger interaction between dark matter and normal matter. And we can use that same idea we had on the previous slide, but assuming maybe there's a stronger force, which can be much stronger than gravity, but still incredibly weak, and allow us maybe to get lucky and be able to detect dark matter in the lab, without having to resort to going to only gravitational interactions. And if it's the case, as I'll say, we can actually already look for some of these models where you have new fifth forces or something between dark matter and normal matter. So the other piece of this, of course, is that we're really harnessing a huge range of mechanical systems now, so-called optomechanical systems, where we're controlling and measuring mechanical degrees of freedom with light. The most famous example that predates even the word optomechanical is LIGO, where they measure the displacement of their mirrors now beyond the standard quantum limit I talked about, a few dB beyond the SQL, to see these really tiny strains from gravitational waves. But LIGO would be way off this chart. There's now a huge range of systems from grams down to femtograms, here to the masses of single ions or atoms at zeptogram scales. Again, sorry for all the SI units, but you'll see even more. But we can.
Zeptogram is.
Yeah, so I have a whole slide on this, but
Okay.
10 to the minus 24. 10 to the minus 21 grams, so it's the mass of a single atom. So within this range, now many of these things are actually being measured. Really, their position can be measured at this standard quantum limit, and in some cases beyond. So there's, we're able to squeeze the light fields or things interacting with these to be able to arrange the measurement in a smart way that we're going beyond the standard quantum limit. So in this talk, I'm not going to be focusing on all of these, but I will talk about optically levitated systems and things in the nanogram mass scale, which might be nanometer size to microns in size. But this is a small set of such technologies because dark matter essentially can be anything. You can also use these systems for many very different models of dark matter than what I talked about. There's a recent white paper talking about this. So this is our group working on these experiments at Yale. So we really are a small scale experiment compared to many dark matter searches. We do have an acronym though, so it can be an official experiment, but it's a few folks and 2 optical tables sitting in our lab at Yale. So it's kind of amazing that you can trap, nano to micro-sized particles with just take any laser you have in your lab, basically focus it with a lens or an objective, and depending on the size of particle you want to trap, maybe you use an objective and focus it to a really tight focus here. And we can trap particles from a femtogram to a picogram on these kind of highly focused optical tweezers. Here you see a femtogram mass particle that in the picture I showed at the beginning. And we can even go larger than a picogram. We can go up to 30 nanograms or so by building this kind of levitation style trap where it's confined by this focused laser in the perpendicular directions of the beam, but the vertical direction is just lifted up from the radiation pressure of the laser against gravity. And so, from scales of femtograms up to nanograms, we can just, stably trap dielectric particles essentially as long as we want in the lab. We could go even higher with optical traps, except we found these are the biggest particles actually ever trapped this way in our lab. And they melt because of optical absorption of the laser light. If we made better quality materials, we could probably go up to micrograms or even larger. Once you have these things trapped in the laser, you can pump these things out so that there's no thermal noise essentially from background gas collisions. So in biophysics and biology, this is an extremely common tool. And we've really revolutionized how we measure piconewton scale forces. It's all these kind of motor proteins and really nanobots walking around in biological systems that we've learned about using these kinds of tweezers. But in those systems, you're always sitting in a thermal fluid at room temperature, so you have Brownian motion and thermal noise. If you just go to vacuum, pump the air out of the chamber, you get rid of those thermal collisions. Your particle basically doesn't know that the walls of the chamber around it are at room temperature. And you can get to these limits where you're really limited by the photons interacting and the measurement of the sphere's position by these optical fields rather than some sort of thermal fluctuations. And you get to force sensitivities for these relatively large objects, again, 10 to the minus 21 to 10 to the minus 24 newtons, yocto-newton scale for femtogram particles, and zepto-newton scale for these larger particles. Again, I'll show a plot putting this all in context. Next slide. But in addition, this really comes from these things being thermally isolated, not having thermal noise. It's also really crucial these are electrically isolated extremely well, and we can control the electrical charge state of these particles without currents kind of flowing, taking charges on and off these particles. So they're also electrically extremely resistant. And so, of course, Arthur Ashkin got the Nobel Prize, or half the Nobel Prize, a few years ago for actually exactly this sort of levitation trap that we now have a modern version of in vacuum in the lab. So yeah, so to put the SI units in scale, this is kind of a fun plot from based loosely on the Wikipedia page called Orders of Magnitude in Force. So this is showing forces from the meganewton scale here on the right side of the slide, where you have the Saturn V at liftoff at 10 meganewtons, down to the weight of a single grain of sand. Again, these optical tweezers that work in fluids that really have allowed us to measure all these really interesting mechanical biological systems. Here you can see kinesin, or at least an animation of kinesin walking along this microtubule. It's a real biological system that pulls along this, this large polymer behind it. And we've been able to learn all about that with these kind of very sensitive tweezers in fluid. If we get rid of thermal noise and go to vacuum, though, we can get down to these attonewton, zeptonewton, and yoctonewton scales. So maybe zeptonewtons here are 10 to the minus 21 newtons. And just to put this in context, this is now the weight of a single virus, the gravitational force between microscopic objects, micron-sized objects. And the kind of hierarchy and scales here, the forces are another 9 orders of magnitude smaller even than those fluid optical tweezers. So that's kind of the same hierarchy between the Saturn V liftoff and maybe the weight of a single grain of sand or something. So these are really tiny, exceptionally sensitive detectors. So with these,
You're not saying that those forces have been measured, are you?
we have measured, yeah, we are measuring forces in these systems at these levels. Yeah, and I'll show you some examples, and that's the theme of the talk, is that we can measure these forces. Yes. Yeah. So maybe, so I did calculate in natural units, so a milli eV squared here is at an attonewton. If that makes you more comfortable, to me it's much less comfortable, but this is, you know, these are really, really tiny, tiny, tiny forces. And as also, I will switch to natural units when we start talking about momentum impulses. We can start to measure the momentum carried by single fundamental particles, dark matter, for instance. Okay, so this is what the setup looks like. As I said, it's a tabletop experiment. We have a vacuum chamber here in the center. If you've ever seen a cold atoms lab, there's many fewer optics on the table than in those labs. These are relatively simple AMO experiments. We have a laser, some optics just to vertically orient that laser in this case, focus it in the center of this gold-coated cube in the center of the vacuum chamber. And then we just take the light scattered by the particle. That light carries information about the position of the particle, and we do a weak continuous measurement of the position of the particle that allows us to infer its momentum with some position-sensitive detectors on the output side. So this trap here currently is being upgraded. So we typically have trapped kind of one particle. Again, we can trap between 100 nanometer up to 30 micron scales, but we're working towards arrays of tweezers. So once you have one, you might as well make a lot. So we're currently, we have 100 focus beams in the same trap now, and we're trying to load 100 particles into them. I'll say a little more about that. And once you have them trapped, these things are really stable. They'll sit in there. The trap depths are like 10 to the 5 Kelvin, so you can just keep that particle for as long as you want until someone drops a wrench on the table or the power goes out or something like that. And we've had single particles for more than a month at the base pressures of our system. To give you a little bit of a flavor of how this all works, you know, there's lots of steps to make this work. So the first thing is you have to get the sphere in the trap. If you're in a biological tweezers, they float by in the fluid. You move your laser over and you grab them. If you're in vacuum or in air, they would just fall. So we actually put them on a glass slide. They're like dust particles sticking on a glass slide. Van der Waals forces really want to hold them on. You just shake that slide extremely fast, like accelerations of 10 to the 6 meters per second squared or so. But we put our laser over top it, shake it with a piezoelectric transducer. You're actually seeing a video here. It's in focus when the thing's sitting on the glass, and it pops up into the trap, which we're holding it up above the focus with the laser, and then we can lower it back down and actually pick the same particle up over and over. Once we have it trapped, we can move that glass out of the way, and we can pump this down to low pressures. This is a plot of, now we put electrodes around the trap, we apply an oscillating electric field, and measure the correlation of the motion of the particle with that oscillating field. Of course, that tells us about the net electric charge on the particle. When we pull these things off glass, because of just triboelectric charging, rabbit fur on your glass rod sort of stuff, they always start with a pretty significant kind of negative electric charge. So about 10,000 x6 electrons over protons. But then we shine UV light and knock electrons off that particle. And here you can see the correlation of the motion decreasing as we reduce the net charge of the particle. We even go past 0 here, which means we knock too many electrons off. Now we have more protons than electrons, so we start knocking electrons back on from the neighboring gold electrodes, start going the other way, and here when we get down to, single steps, knocking one electron on at a time onto the sphere, you can see very clearly here, and even a small electric field, 1 volt per millimeter, in a 1 second measurement, we're resolving these forces that are as small as 200 attonewtons here with really high signal windows. So we're measuring really tiny forces as we knock single electrons back onto the sphere. Now, the good thing is at this point, right, we have an object that has 10 to the 15 electrons and protons on it, and we know it has exactly the same number of electrons and protons, so we've got rid of our highest order coupling to background electric fields and other things that could give us problems. Of course, the monopole charge is now 0, but there can still be multipole moments in the electric charge distribution that couple to various stray electric fields and other things we don't want. So now we start spinning the particle. We actually use circularly polarized light, and we transfer a little bit of angular momentum each time from each photon to the particle. Because the damping is so low in vacuum, this thing will just spin faster and faster over the course of a day. We're showing the rotation speed as a function of time over a couple days. And you see it spinning up to many megahertz, so this thing's spinning millions of times a second. If we went any faster, it would actually explode from centrifugal stress. So what limits how fast it spins is just the strength of real materials. So micron-sized objects can go to megahertz. Nanometer-sized objects can go to gigahertz. We've now made
you measure the frequency by the irregularities somehow?
You can. We use polarized light, and we just see a rotation of polarization as it spins. So the irregularity will give it some geometric birefringence, which causes that polarization to change, or it may have some net kind of built-in birefringence just because the amorphous structure is not perfectly amorphous.
Right. It's some sort of inhomogeneity.
Some sort of,
that is
either in the
giving you
shape
that-
or in the actual kind of optical axes of the object. Yeah, exactly. And so we can just, shine polarized light on it and measure very precisely this peak moving in frequency as it spins faster and faster. And these are the fastest made, human-made spinning objects that we know of, just because they're small. But these things are, the reason to do this for us is it gyroscopically stabilizes this object now, so that if it has any multipole moments, we now average those away, so we only have a permanent electric dipole moment along the spin axis, and that axis is very well stabilized. It has a ton of angular momentum, so it's not going to be wandering around. So I'll say in a second we can even control it. So this is, orienting that dipole moment. If we want, we can also cool the effective temperature of the center of mass degrees of freedom. So when this thing's just sitting there after we've pumped it down from room temperature, and if we measure the power spectral density of the motion, let's say in the direction perpendicular to the beam, this is the amplitude of that power spectrum in meters per root hertz. So this is a nanometer per root hertz here in the center of the plot. You can see when we start out here, we have a relatively high Q. This is the kind of transfer function of a damped harmonic oscillator. We have a high Q resonator. And then we actually watch the motion of the sphere. When it's moving to the right, we push a little bit back on it to the left to cool its motion. And with active feedback cooling, we can cool its motion so it's as still as though it were in a thermal equilibrium with a 50 microkelvin gas. So you can't actually cool all the internal degrees of freedom of any such large object to this temperature. But we can, for that one very special degree of freedom, the center of mass of that entire particle, we've made it as stable as though it were cooled to this temperature. With a noiseless feedback mechanism that doesn't have noise. So we have that's another way to say that this thing has essentially no thermal noise or is extremely well isolated from the room temperature walls of the container. And then the very last things, I know this is a lot, but the last thing, if we want to, we have this dipole moment still, which could couple to stray electric fields. We can do the kind of electrical classical analog of a pi pulse in NMR, where you have a magnetic dipole and you can flip that thing over by applying a torque. Here, if we apply an electric field perpendicular to that dipole moment, we can take this megahertz spinning object and flip its spin direction over. And we've shown we can actually average away residual couplings to these dipole moments. And this, again, is crucial because electric forces are so much stronger than gravity or the other really weak couplings we're looking for. If we have any stray couplings to electric fields, they can be and they are the dominant backgrounds for these switches.
For your fourth step, after you cool down, how long does it? Let's say then you turn off the laser. How long does it take to thermalize back to room temperature?
Yeah, so the reheating is provided by the laser too. So there's a heating rate and a cooling rate from our laser, and when we turn the cooling as high as we can, we get to this equilibrium temperature. we turn it off in this system, our reheating rate is like 10 hertz. So, it goes back up, essentially immediately. So you don't actually win. So this is kind of cute. If you want to cool to the ground state of the potential, you can do fun quantum things this way. But this doesn't help with our force sensitivity because that heating from the laser is always there, whether we're cooling it or not. So what we really care is this shows that we're at a really good level of isolation, because when the heating and cooling are kind of at their equilibrium here, we're getting to very low temperatures. It's subtle, so we can chat about it. So anyway, so this is lots of technology. This all, basically has come together over the past kind of 6 or 7 years. So, but at this point, we're really now applying these to fundamental physics measurements, which I guess is the fun of the rest of the talk. Before I get there, I'll give you one more slide on SI units because it's kind of cute. So it's interesting that for the first time in many decades, there's new SI units just from last year. So there's at the high end of the scale, there's Quetta and Rona. And this was motivated by really big data. So people were making up names for like telebytes and things up here, and the metrologists really don't like that. So they said we have to get together and convene the community. And so they added 10 to the 27 and 10 to the 2030 and 10 to the 30 for kind of motivated by this. But I think this quote is interesting because it says, there's a very thoughtful article with the SI folks talking about this, and then they say, we added these little tiny units as well at 10 to the minus 27 and 10 to the minus 30. We're not sure that anyone's actually measuring anything at that scale, but it's better to have the scale balanced. And I would say once we get these spheres neutral, we actually have seen that they stay neutral and there's fewer than 1 electron flowing on or off of them in a few weeks. And so in some funny way of thinking about it, that's an average current here of 10 Ronto units. So there's at least one example that I know of where there's something that ends up in these low Okay, so with all that in place, what can we do for maybe fundamental physics measurements? That's really our motivation in our group. So the obvious things when you have a good force sensor are to test fifth forces, Newton's and Coulomb's law. We're generically interested in this. These are really hard experiments. It's not obvious we can beat the kind of torsion balances, but we're working on it. And the group at Stanford and Georgia Grada's group is also working on this systems, and Andy Geraci at Northwestern. We're also interested in testing Coulomb's law. It looks like you could do interesting tests in the kind of micron range of Coulomb's law that haven't been done before. We have done with these particles that have 10 to the 15 protons and electrons in exactly the same number. We have the world's best limits on fractionally charged particles bound in matter. So we can ask, is that ball of stuff exactly neutral once you get it to a net integer charge of 0? And we found that we've done searches where if there was even one particle with a charge above 10 to the minus 5 electrons per 10 to the 17 nucleons in our sphere, we would have seen that in these searches for fractionally charged particles. If you take the kind of expected terrestrial, if dark matter had some charge component, you take the expected terrestrial accumulation, this would probe charged dark matter fractions down to 10 to the minus 7 of the relic dark matter density. So we haven't seen this, and we can keep pushing on these, but there's no obvious evidence for a charge component of dark matter, at least locally at our part of the galaxy. You can also test charge quantization, the sum of the proton, neutron, and electron charge. We know experimentally that those have to be less than 10 to the minus 21 electric charges, but that really comes from.
I have to really complain. You ought to have axes on your plots. Otherwise,
Yeah,
it's just a picture.
This is just a picture because I don't have time to talk about these, but I'm happy to show you the axes and stuff.
But just as a generalized complaint. Next time we give a talk, please do that for your audiences.
Thank you, yeah. So this is literally just a picture, hopefully to get you excited to look at the paper. The archive number is here with the axes, so I'm only going to say one sentence about it. But yes, the problem is the axes are so small that I think they're distracting in this case. But let me talk about this, which is what I'm going to actually focus on this talk, which is trying to detect little tiny impulses, little kicks to these particles as some dark matter particle or other interesting thing happens in the sphere. So there's kind of two cases. I'll start with kinematic detection of dark matter. This comes back to that idea at the very beginning of the talk that you have some maybe composite dark matter particle flying by one of these little trap spheres. There's some now new long-range fifth force between dark matter and normal matter, stronger than gravity, but still very weak. That gives a little momentum transfer to the particle, and then we see the entire particle recoil. Or we can implant maybe alpha and beta emitters into these particles, have, let's say, beta decays where beta particle leaves, and then maybe an invisible particle like a neutrino or other invisible particle leaves, and we can reconstruct that by measuring the recoil of the sphere and the free momentum of any emitted particles. So these are a few papers thinking about these ideas. So let me start with this kind of idea of kinematically detecting dark matter and particle dark matter flying by the spheres. So we basically pick up at the end of that experimental slide where we have this trapped, cooled, spin stabilized, spinning at a megahertz nanogram mass sphere. If these units are useful at that 50 microkelvin, the kind of center of mass energy is 20 nano eV. So this is really a stable object sitting there in the center of our vacuum chamber, and we're going to look for this dark matter particle to fly by and give it a little kick. So we're just going to assume there's some generic new fifth force between matter and dark matter, which we don't really care about the exact, microscopic description of that, but it gives us a long-range force with a Euclid potential, where we're going to write in our notation the coupling to a single neutron here is alpha n. We have some number of neutrons in our sphere, which we call n sub n. And then if there's a massive mediator mediating this interaction, we have a length scale for that interaction that goes like 1 over the mass. So this can be anything, whatever you like. But the key thing here, right, is that we have lots of constituents in our particle and maybe also in the dark matter composite particle. And so the cross section for this goes like the kind of number of constituents we have squared compared to the cross section to scatter from a single neutron. So because we can have something like 10 to the 15 neutrons in let's say a 10 nanogram mass object, this number can be very, very large, maybe even rivaling Avogadro's number. So you should be asking how the heck you can do a dark matter search with a nanogram of mass when our standard dark matter WIMP searches are, tanks of, tons of xenon or something like that, which are really benefiting from having lots of neutrons around. We're doing it here. Of course, those xenon detectors would be having all kinds of scatters from these types of dark matter particles, but they wouldn't be transferring enough energy to a single nucleus to see it in the xenon detectors, whereas we might be able, if the primary interaction is with clumps of matter, we might be able to see it with these types of experiments. So it's kind of a completely different set of dark matter models than you can look for with the kind of normal WIMP detectors. Okay, and just to say, maybe this is the most interesting thing to folks here, but I will say that we didn't invent such models. You can find models of this type that would produce these kinds of phenomenology in the literature. This is not a comprehensive list, but some relatively recent examples where you might have composite dark matter interacting with normal matter through a long-range force. So what does the experiment look like? So again, we want to see these little kicks to the motion of the sphere. We're doing a continuous measurement of the position of the sphere. So this is the displacement of the sphere as a function of time, where we've put one electron back onto the sphere. We've turned on a short electric field pulse that gives just a momentum impulse. Because the dark matter is flying by in less than 5 nanoseconds, our sensor isn't fast enough to resolve the collision, just sees an instantaneous impulse where we see this damped harmonic oscillator response after the kick happens. And so, this is a nice experiment. We don't have to use a radioactive source or something to push on the sphere. We can just put that electron on there and with exact known force push on the sphere just the way that dark matter would, and then calibrate the response of our force sensor to that. Just watching a mass on a spring rain after it gets hit by a dark matter particle. Because of this, we can also very easily measure our signal efficiency. So as we increase the size of this electric field impulse that we're applying, we can measure whether we can reconstruct these things. Obviously, when they fall down into the noise, we can't see them. If they're much bigger than the noise, we can. And for this experiment, this is really a proof of principle, but for this experiment, for momentum transfers above a GeV, and GeV per C, where C is 1, we're able to actually 100% of the time see kicks. And we've switched from SI units now to really fundamental particle units, kind of the momentum carried by, let's say, a TeV dark matter mass particle flying through the galaxy at 10 to the minus 3 C. So this is, really individual particle, fundamental particle momentum transfers that we can see in these macroscopic objects. The other interesting thing is this is a bigger particle than we'd like for this, but if you look at our threshold here, we're sensitive down at the kind of 100 MeV scale. It's 10 to the minus 20 kilogram meters per second. And if you think about the momentum carried by a single alpha particle leaving on nuclear decay, we should be able, with this exact same sensor, to be able to see alpha particles the nucleus recoil after the alpha particle leaves, and then the whole entire mass that single nucleus was in recoil with that kind of momentum. So for this time, I'll talk a little bit about that. Okay, so just to show we could do this, after we got back from COVID, actually back into our lab in 2020, we did a proof of principle search where we just let one of those spheres sit in the center of the chamber. We measured the rate of impulses that we see, counts per GeV in momentum per day versus the amplitude of those reconstructed impulses. The gray line here is all the events we see, and you can see there's our Gaussian noise here. This is a log scale, and then there's also this tail of many large non-kind of random impulses to the sphere. It turns out, though, that because it was COVID, we had this log of when people were in the lab. There's one specific postdoc who was responsible for many of these impulses. It must have been our loudest postdoc by far. So when we cut out the times that people were in the lab, we get down to this gray line. We can also put an accelerometer on the table, which sees other sources of noise. So there's a lot of acoustic noise if someone talks in the lab. The sphere actually moves by nanometers. That shows we haven't isolated it as well as we could, but it's a background in this first search. And once we cut out all the things our accelerometers pick up, we only look at times when people aren't there, dropping wrenches and things. We get down to these black points here, which mostly follow the expected Gaussian noise, and then there's about 4 events here in this tail that could be candidates for dark matter impulses that weren't correlated with backgrounds we knew about. Now, of course, though, we've cut a huge number of backgrounds away. This is the first search of this type. So we're being conservative here and assuming that these points could either be due to those backgrounds that we haven't fully eliminated or due to some dark matter signal. And that allows us at least to put limits on some generic dark matter neutron coupling of the type. I was talking about this fifth force between dark matter and neutrons. This alpha n, as I was describing before in this general framework, but if you want to assume a microscopic theory, you can relate this to the couplings in that theory to neutrons versus the mass. And then we get the strongest limits when we have a truly long-range force that coherently interacts with the entire particle without a form factor. That's the massless mediator here. But for more massive mediators, we still have sensitivity up to mediator masses of order in eV. So these are still extremely light, but that's kind of roughly the inverse size of our particle. And we're sensitive to really heavy dark matter masses. Again, we're seeing GeV momentum transfers. So we need the dark matter mass to be massive enough that it can carry that much momentum and transfer it to the particle.
Question. Yeah. How do I understand the amplitude in GeV unit?
So this is impulses in GeV per c. So because we're truly measuring magnitude of 3 momentum, which I'm measuring in GeV per c.
So it's not a displacement or something.
This is what we truly measure is the displacement in nanometers, and then we calculate for what momentum kick at time 0 that we've gotten the displacement of cell. And so this plot tells me then the momentum kicks in the cell.
So like one point is, you say the detection, the signal depend on the dark matter kicks the particle trap inside. So does this depend? Does the measurement depend on the phase space distribution of the dark matter, or not? I mean.
Yeah, for sure. So this assumes the standard halo model, which we can all debate, but yeah, this calculation when we go to these limits here assumes the standard halo model.
So it's like 10 to the minus 3.
Yeah, 10 to that's so if you have a TeV particle. 10 to the minus 3, that's why you're seeing kind of TeV showing up here at the minimum sensitivity. That's our GeV.
Presumably your sensitivity falls as the mediator mass gets big again. That must be your peak sensitivity around DV,
Yeah.
and that's why you picked it, because as the range gets shorter and shorter, they would just completely miss each other.
Yeah. So that's what you're seeing in the colors here. The light mediators, the truly massless thing is the best thing, and then if we start to have some mediator mass where the inverse mass is smaller than a particle, we get a form factor suppression, and for masses bigger than an EV mediator, this completely cuts off with the size.
How do you tell apart from alpha decays?
So we don't have any alpha decays happening in the sphere. Because it's such a tiny amount of mass, we would have to put those alpha emitters into the sphere, which we're doing. But in normal material, it's a femtogram, you just don't have any natural radioactivity. Yeah, so I really like this question because we think about it a lot. In this like 10 to the 15 atoms, you have a part per million uranium and thorium, but because the half-lives are so long, you don't see any natural radioactive decays coming from the particles. The ones from the walls just miss it because it's such a tiny cross section. So we really would love to have alpha emitters in here, but we need to put them in ourselves. From data line.
Can you give me some insight into what your backgrounds are and how you're modeling them?
Yeah, so we're not modeling them all because they're the worst backgrounds. They're like people talking next door or walking above the lab.
Right, so I know
Yeah.
that that's your cuts, right?
Yeah.
So like getting people on the lab, but then
Yeah.
if you, after you place those cuts, do you have other backgrounds that you look at?
So we, as far as we know, the dominant backgrounds for this experiment are acoustic and vibrational noise in the lab, which we can only measure, and we have not gotten to the level of sophistication we can model them. So our plan is to shield those more and more. LIGO has done an extremely good job. We don't have to be as good as LIGO, but we'd rather just get rid of all those backgrounds so we don't have to model them, because we tried to get a record of the people walking over the lab, but even that's like hard to do. So there's a lot of room here to improve by just not being sensitive to acoustics.
And cosmic rays and all that.
Cosmic rays will never hit the particle because the geometric cross section is too small. We get 1 muon per year. So in this 5 days, we can see it.
Can you shoot things at your ball?
Yeah.
Like electrons? Or-
Sure, you could focus electrons and shoot them at them. We think, I'll say, maybe more interesting though is to hold interesting nuclei inside the sphere. So it's a way for a laser to confine decaying nuclei in a well-localized place and use that just as a way to hold interesting things on the nuclear chart. But you could alternatively shoot things at the sphere and measure the momentum transfers.
Could you shoot something that only gravitationally interacts?
Yeah,
Something
shoot a
like
dust
that?
particle next to this and see it. Yeah, I think we did some estimates of that. That would be a fun experiment to do. I think even with a pretty massive particle, so we can see like a millimeter mass gravitation interaction from like a millimeter piece of lead next to this at our kind of current sensitivities. That's a hard thing to do though, and we haven't found a good motivation to do it, but it would be fun.
So in your limits, so if you have a meteor that couples with, let's say, 10⁻⁷ Yukawa coupling to neutrons, you would have stellar cooling limits. Right?
Yeah, so sorry to interrupt, but I mean, we've done this in a funny way, which maybe is misleading. We're lumping the number of constituents in the nugget into that to be experimentally agnostic. But you're right, you would hit all kinds of, for this proof of principle search, the only way to get to some maybe viable models is to have composite particles, right?
So you're looking, so basically you're looking for composites, right? Your physically irrelevant limits are
For now, this thing, which is like 5 days with the sphere we had in our lab, but let me show you the product. We have big dreams to go to single composite particles. Yeah, so I'll also say pretty quickly, if you want to assume a specific composite dark matter model with some viable coupling, so there's a paper from Catherine Zurich's group that does this, and in those models we can convert to your standard WIMP kind of dark matter neutron cross section on more conventional units versus dark matter mass, and if some composite object like this were a fraction of dark matter, 100% of dark matter, you get some limits from the previous plot, translating to a model-dependent kind of framework. The canonical WIMP detectors are way off the top of this plot because you basically never get a hard enough single nuclear recoil. We'll have some nuclear recoils, but they aren't high enough energy to see them. So they're like all the way up at 10⁻⁻⁻ centimeters squared or something completely unviable. So the biggest kind of limits here come from Edwash, which constrains, of course, neutron-neutron fifth forces. You have a neutron dark matter fifth force, and even if you crank it up maybe as high as you're willing to have a dark matter coupling of ordered unity on one side, half that Edwash diagram still sets some sort of model-dependent bound. And so we just picked a model where for a specific constituent, very light constituent mediator, we get a little bit below the Edwash bounds.
Sorry, I have another naive question. So do you expect, because I really know the microscope have a little bit stronger constraint than Edwash.
Yeah, so if you go to heavier mediators that Edwash would not be sensitive to, or shorter range forces, then this thing goes away. But for that particular size sphere we had.
So sorry, I mean, what I mean is the microscope satellite seems.
Oh, the microscope satellite.
Yes,
Yeah,
yes,
so that's
let's go.
very light mediators. They are, for
I
equivalence
see.
principle
0.5.
violating things at extremely light mediators, they'll be the best.
Yeah.
But for kind of lab scale mediator masses, Edwash is the best. Okay, so let me say one more thing and then I'll advertise where this is going. So the key idea here was that if you want to use a tiny amount of mass like this and get some dark matter relevant rate, you need to coherently interact with the entire particle. You don't want to hit one nucleus in the particle. You want to push on all the nuclei together so that you can get a substantially larger cross-section off the particle than you would off a single neutron. One way to do that is to have a truly long-range force like I was talking about. Of course, the other way we talk about coherent scattering in dark matter searches is the standard thing with WIMPs, where the momentum transfers are small enough, they don't resolve the substructure of a single nucleus, and even heavy mediators in that case, we have our normal weak interactions with heavy mediators, you can coherently scatter from that entire nucleus because you're at low enough momentum transfers. You can ask if you could take a WIMP and coherently scatter from not just a nucleus, but an entire nanometer scale chunk of stuff. And it turns out that if you plug in the numbers, it is actually possible to get coherence over an entire maybe 15 nanometer sphere. So this is smaller than the spheres people are tracking now, but definitely possible if there's a good motivation to go to it. If you're able to get down to momentum sensitivities kind of at the standard quantum limit and maybe a little bit beyond the standard quantum limit, that Heisenberg uncertainty for measuring these recoils of the spheres, then you can see these kind of momentum transfers from very light masses, so now not TeV, but maybe MeV down to tens of keV masses, where the momentum transfer to the sphere is low enough that you coherently scatter off this whole chunk. And again, you get this coherent enhancement of like, now maybe in this particle 10 to the 7 or 10 to the 8 constituents squared. It's not quite Avogadro's number, but you can still reach dark matter relevant cross sections. So this is very ambitious. Maybe closer term is these solid lines, but if you really push this and turned everything up with 10,000 particles, 1 year exposure without backgrounds, a little bit better than the standard quantum limit, you could actually get down to approaching picobarn cross sections for 10 keV sort of dark matter masses.
Sorry to talk so fast,
Yeah.
it's hard to assimilate it all. But you must be making some assumption, and you probably even said, about the mediator here.
So this is any heavy mediator. And so we're getting coherence regardless of the details of the mediator by transferring such little momentum that we don't probe the substructure of the particle. So the thing we like the best is like, coherent scattering of neutrinos from nuclei. Like if they're exchanging a Z, they don't know which nucleon they're exchanging that with. They coherently scatter so the amplitudes add up and then you square it. It's the same idea, but now with a quote unquote macroscopic or nanoscale object. And so yeah, sorry for going so fast. Definitely stop me.
And that's why it's decoupled there, right? So as you go to MEV, you lose it because you're not coherent over the full
your
sphere.
form factor is cutting in and cutting this out, exactly. And then the momentum threshold cuts it off. So this is futuristic, but who knows? I mean, as a community, we're working towards this, and it's not. There's lots of plots now that have projections down in this sub MeV range. Here's another projection plot.
So all of these are projections?
These are projections,
Oh,
yeah, I
sorry.
apologize. So the thing I just showed, these are real limits, but this is a projection. Okay, so what do you really want to do if you want to make this work? So the thing I showed that's not a projection is really proof of principle. So again, these technologies are kind of brand new, so we're just getting started applying them to fundamental physics, even developing them, let alone doing fundamental physics with them. So there's two things we want to do. We want to, for the bigger particles, so at the small particles, we're at the standard quantum limit. For these big kind of nanogram mass particles, you want to push to the SQL. And then once you reach that standard quantum limit, you want to go beyond it. So you want to do smart quantum measurements that don't learn about the position, only learn about the momentum. In principle, at least, you're trying to measure momentum. Momentum commutes with the free particle Hamiltonian. There's no quantum limits to how well you can measure the momentum in these systems. There's definitely practical limits to how well you can do it though. So we don't know, kind of where you can get technically. The other thing though is just once you have one, make a lot. And there's a huge kind of burgeoning field of making arrays of optical tweezers. These are now technologically relevant for quantum computing with Rydberg atoms. There's literally billions of dollars flowing into doing this with atoms. They're going to need to get to millions and tens of millions of Rydberg atoms to make useful quantum computers. So it's likely we'll have technologies to keep making these bigger. But I guess so far in fluids, we have lots of, actually here, even at NYU, there's large arrays of fluid-based optical tweezers from long ago. Cold molecules we now have, and here's 3 so far at Yale, but we're working in the near term to kind of a 3x3 and then a 10x10 array. So of course, when you're doing dark matter searches, the more targets you have, the better. So you can go to lower and lower cross sections as you push up the size of that array. The more targets you integrate for longer, and then you can go to smaller and smaller momentum transfers and smaller dark matter masses by pushing down the threshold of these detectors. So smaller particles are going beyond the standard quantum limit. Again, on this kind of weird coupling I defined, that proof of principle search is here in blue. But then to Ken's question, you can get down to single particles at the Edwash bounds. If you go another 4 orders of magnitude, which really does look very, because these are brand new things, really achievable. And then, at some, if you leave some bounds on compositeness at some masses, they're always composite or maybe single particles down in this corner of the bottom. So this is, this is ambitious. It's beyond where we are now, but these are real projections that you can imagine happening. And they can look for dark matter models that otherwise, maybe they're not the first ones you write down, but otherwise we don't have technologies really in the lab to look for.
And this is the fundamental coupling to the neutron.
Yeah, so when you get down here, if you have
multiplying by the number.
Yeah, so what that kind of single particle line means is that if you have one neutron and you have the Edwash bound on the kind of neutron fit force, there's no limits from Edwash below this. You can proceed.
And here it cuts off at 1 GeV, but the previous one was at tens of keV, right? So you're this is a heavier.
These are big particles. Yeah.
Okay.
You can make the same plot for little particles. It will push higher in cross section, push way to the left. So whatever you like, we can make a particle of that size and do a search. This is one example. I apologize, it's not really hard to attend. So I have been talking, let me just say, so these are for free directional detectors. We're measuring momentum, we're measuring 3 momentum. So if you do see a signal in these detectors, it's definitive because during the course of the day, you see the recoils coming, opposite our proper motion through the dark matter. So, big goal of the field is once we see a signal to make a directional detector that really sees this. If these are the types of models and these are the right detectors for them, we won't have to build another detector, we'll just know it right away. Or if we hit backgrounds, we can keep going by using this direction. So I have been talking fast, so thank you for asking lots of good questions. So I'll only advertise this kind of last idea, which is also ideas, but not yet experiments, but searching for other invisible particles, quote unquote invisible particles. The idea here is instead of having dark matter scattered from the particle, exactly the same sensor I was just talking about, we can put nuclei of interest. The most interesting ones in the near term are ones that emit neutrinos. And in the simplest case, maybe choose an electron capture, where you capture an electron from the K shell of the nucleus, the atomic cloud around the nucleus, you emit an electron type neutrino, and then the nucleus, of course, recoils with equal and opposite momentum to that neutrino. Maybe for your normal electron captures, that's like an MeV of momentum, so not a GeV, but an MeV. You can do this with 100 nanometer particles. And then that nucleus stops in this glass particle, and the entire particle moves when that nucleus stops. Does some really complicated thing, but by momentum conservation, we know 3 momentum is conserved. And whatever happens, that entire center of mass degree of freedom is special and is going to move with the essentially opposite momentum to the neutrino. So if we can measure the 3 momentum of the sphere well enough, we can reconstruct the 3 momentum of the neutrino. Of course, look for anomalous things. So we can measure the momentum of the neutrinos, we'll say with high signal noise, and see if it's ever not what we expect. So there's a new paper, relatively new paper, describing these ideas. So compared to the previous thing, now you just put kind of traditional charged particle detectors around the trap so that you can maybe see the Auger electrons and X-rays that come out, or the beta that comes out of the beta. I will skip this, but the first target for this would be sterile neutrinos. There's a huge unexplored parameter space. Sterile neutrinos around 10 keV are a plausible dark matter candidate if they couple weakly enough to the or mix weakly enough with the standard model neutrino. So this is essentially the branching ratio, the mixing with normal neutrinos, the element in the PM&S matrix. If you have a heavy sterile neutrino versus its mass. So in our nuclear decays, we get most of our decays would be to the light neutrino states, but with some probability here on the vertical axis, you'd see a heavy neutrino come out sometimes. And so we can look for these, and the best kind of current limits for nuclear decays come from looking at beta decays, exactly the sort of things I'm talking about. We're looking for a kink in the beta decay spectrum. Here we would be looking event by event for a sterile neutrino to come out and see an anomalous momentum come out. Just to show this would be pretty, blinding signal if we see it. We have good reason to think this can be very low background. So we essentially wouldn't have backgrounds in this experiment. We put argon 37 in, so we get about 1 decay every few minutes. We reconstructed the momentum of the neutrinos coming out. Most of the time, a light neutrino would come out, and we'd see this peak with momentum at the Q value. But if we zoom in down here, lower reconstructed momentum, the sterile neutrinos were coming out at the current best laboratory limits. In 1 month of data, we would see a peak like this. This is again a projection, but we would see a very clear evidence for heavy neutrino with these existing sensitivities. All we need to do is get the right isotopes into them. Again, this is too fast, but I'll just say that you can translate this into projections, and we can maybe go, depending how large arrays you're willing to consider, many orders of magnitude beyond the best laboratory searches for sterile neutrinos in this case. And this is completely generic in that any invisible massive particle coming out of a nuclear decay would show up here, but we've done it for the specific case of sterile neutrinos. You can ask me about it, but I'll stop maybe here since I'm at time. You can ask the question, can you do light neutrinos? This is really blue sky beyond the state of the art. There's real fundamental constraints from Heisenberg uncertainty that the Ptolemy C/V experiment has also recently learned about. But maybe, I would say, you could imagine in these systems measuring the momentum transfers from light neutrinos. But you don't need as much squeezing as you need for gravitational detection of dark matter, but you need a lot of squeezing. So let me stop there. So I think these kinds of systems I talked about are a small fraction of the optomechanics work. It's really undergoing lots of new technologies. I think there's maybe even lots of applications in fundamental physics. We showed a proof of principle search for dark matter, but the real power of this technique comes in the future as we maybe even get down to seeing coherent scatters from entire nanoscale particles. This ultimate goal of doing gravitational only detection of dark matter particles is still, maybe probably impossible, at least extremely far away. But even if we don't get there, I think there's lots of interesting stuff to do. So thanks very much.
So is it possible to produce magnetic moment for this particle to do something with spin polarized independent forces?
Yeah, so that's a great question. You can, in principle, use magnetic optical materials. You can magnetically trap polarized particles. So I think all these things are possible. We haven't considered them yet because we've been looking for things coupling the mass first. But then once you've done that, you do other things.
So in one of your very first slides, you explained how you had to do all these crazy things to get rid of all the multiple components to the electric field. Alternatively, potentially you could also measure like dipole moments very precisely, or
yeah, so you could. So we actually thought about this. You could look for things coupling to dipole moments, electric charge, stuff like that. I think though you're never going to beat a trapped ion for that because the charge to mass ratio for the ions are much better. So things coupled to mass, kind of nanoscale objects are good. If you want something that couples a charge, well, I mean, we wrote a paper by using trapped electrons with some of the folks making electron traps. And for like millicharge, there was even a paper from Dima Budker and some other folks on setting limits from ion traps on millicharge particles, other things that couple to charge, using the same sorts of ideas. These are probably, silica things are probably not the best for charge, but you can, to some extent, we can put 1 million charges on them if we want. There'll still be less charge to mass ratio than ion.
So what is the minimum momentum transfer can this kind of test?
Yeah, so that's very particle size dependent thing. I do have the formula here, sorry. Here it is. So the standard quantum limit has a square root of m in it. So you can get to very small momentum transfers. So a nanogram particle might be 500 keV, femtogram is getting towards 10 keV. If you go even smaller, you can imagine at the SQL smaller and smaller transfers. Now, as I said, this is not a limit. It's just because you're measuring position. There's no fundamental limit to measuring momentum, but how far we'll get in optomechanics going beyond these numbers, we don't know yet.
Thank you very much. So this comes to my next question is because you mentioned you can give a very strong constraint on mini charge particle. I have one question is because it seems if we go to the strong coupling region, then mini charge particle when it enters the Earth, it will thermalize with the atmosphere.
Yeah. So there's a lot of, when I showed those limits and to briefly explain them without any units, there's some recent papers asking this question. If you have some subcomponent of dark matter, the Earth sweeps it out over time, builds up on Earth, thermalizes, and then eventually it forms bound states with nuclei. At least the negatively charged particles should, in some region of parameter space, bind to nuclei. That's what we look for. We ask, do any nuclei have like funny Bohr-like atoms with some heavy milli charged particle? We can say there are no Bohr-like milli charged silicon nucleus atoms in our spheres in a part in 10 to the 17.
Okay, but the constraint you give is for the single milli charged particle, right? Obeying the standard dark matter phase space.
Well, there the phase space all washes out because you're just like thermalizing these things on Earth.
Yeah, but what's your constraint mostly about? Because what I naively guess if you thermalize with the room, the atmosphere, then your kinetic energy is the room temperature.
Yeah, great.
So you're much smaller than the energy momentum transfer.
Yeah. So when I didn't talk about those milli charge searches. In our case, we're literally asking how neutral is this clump of matter? Is there even one fractionally charged particle in a clump, in a stable bound state? Maybe the other question is, are there unbound milli charged particles flying around? Actually, if they are, all of our charged particles form bound states, and you would expect negatively charged milli charged particles to also bind with nuclei. They would thermalize and bind. But if for some reason they didn't, you could look for them flying by these systems. But that's what I was saying is that ions, electrons are better targets than the spheres.
It's extremely inspiring. So some of us in CCPP would love to see us get into doing tabletop dark matter searches. Tell us about the technical issues. Could you do this here?
Yeah, so we're actually having exactly this conversation on the way to lunch. So vibrationally, for the bigger spheres, we worry a lot about vibrations. For the lighter spheres, it turns out that they work at 100 kilohertz, and you could do them in any room sitting here. So it really depends on the search, right? Some of this stuff I think can happen anywhere, doesn't need to go underground, all that stuff. So that's for those of us who also work on big experiments underground, this is fun stuff and can be done in a normal way.
There are two other questions. Well, one of them was you sort of said if you have more time, you could tell us about the rolling neutrinos application.
Okay, I could say a couple words because this is actually, there's a lot of interest now in the coherence properties of neutrinos and quantum limits on what you can learn about neutrino momentum. And one of the places that showed up recently is that there's a Ptolemy experiment that's going to have a football field of tritiated graphene. You're going to see inverse beta decay on that tritium. You're going to measure the electrons coming out. So you're already laughing, but the sad thing is for us as experimentalists is that nobody realized for 10 years that that's actually impossible, even as I described it, because if you've confined that tritium in a solid graphene sheet, then the tritium nucleus is localized at angstrom scales in graphene. And Heisenberg told us that if something's localized at angstrom scales, it better have momentum uncertainty that's much bigger than that. So another way to say it is that if this 2 microns was an angstrom, I'd have huge momentum uncertainty on that initial tritium bound state in the graphene, and they never put this quantum grounding into the calculations, and so they can't do it. So this was pointed out by some other folks. Ptolemy now agrees, and now they're going to have nanotubes where the tritium's deconfined at least along the nanotube dimension. What we pointed out you could do instead, which is also crazy, is to take the entire center of mass of the graphene and delocalize it. So you can't do this with a football field, but if I had a 5 nanometer flake of graphene, I put tritium in it. Now I squeeze the center of mass degree of freedom of that graphene flake so that it's in a very narrow momentum state. That means I don't know about the position of the graphene anymore. I delocalize the wave function of the graphene in position space. Our understanding is that you can now have inverse beta decays with the momentum resolution you need. There actually is debate. I would say there's a new paper shows up somewhere else where they're asking about the coherence of neutrinos coming out of solid fuel rods in nuclear reactors. They have the opposite understanding of this. Not to bias people, I think they're wrong, and I can explain why. But I think this is one way to avoid the Ptolemy issue. And you would need to do something like that for sure if you wanted to measure the momentum differences of light neutrinos coming out of nuclear decays in these places. But I'll say that if you could do all this, and you put some really low Q value decay emitting a QeV neutrino, then you could projectively measure, when you do the measurement of the sphere recoil, which is entangled with the neutrino coming out, you're going to collapse the electron neutrino into M1, M2, or M3 through your projective measurement with a probability that gives you the PMNS matrix elements. So this would be a beautiful measurement if you could do it. I would put this as not as bad as gravitational dark matter, but detection, but getting close to that. We can, at this point, we can dream because people really are talking about getting to these kinds of levels of squeezing and stuff in the systems.
I have one other question. Does your lab do other than fundamental physics work? Are there other kinds of applications that you do?
Yeah, so the Navy funds us to make accelerometers, where I guess they think they're going to make nano submarines or something. And then, you know, the maybe interesting thing is the people who put nuclei decaying in silicon nanoparticles. Some folks at Sloan Kettering, they do it for cancer therapies. We want them to make our spheres, and we've been collaborating to help them understand how they want to keep the nuclear recoils in the spheres so they don't leave toxic things in your body. We want to keep them in the sphere so they transfer the full momentum to the sphere. So there's some maybe collaborations there as well.
Okay, there's been lots of questions, so let's leave it again.
Thank you.